Generally speaking, that is not a very good approach to modeling. So because every time you do something, you learn something. So so you want to start off, look at your data and say, if I only had this data, what's the model I can build? If I collect this data, then what else can I do? Then if I collect this data, what else can I do? Every time you do a model, it'll tell you, hey, you probably have a lot of uncertainty here, or you probably don't know much about this here. So then you say, okay, I'll go collect that data. So data collection, field work, modeling should kind of go hand in hand. So sometimes we do laboratory experimentation because some of this data has to come out of the laboratory, but it's kind of hard to look at models in isolation or have preferences for models in isolation. So because we are engineers, we want to solve problems. So our solution should be the goal. What tool gets us there? We'll use any tool that gets us there. So I'm not really a tool-focused modeler. I'm more a solution-focused modeler. If you've written a code and spent a lot of time writing a code, of course you'll be in love with that code. So you will say, I'm going to use that code. So they say that if you have a hammer, everything looks like a nail. Okay, so we want to kind of avoid that when we do modeling. So a lot of people who do physics-based modeling or the kind of modeling I'm teaching here come back and say, well, data-driven modeling is not that good. It's all empirical. It has no theory. I really don't say that. I'm like, if you have data, if it serves a purpose, you should go. There is no harm in doing that. Only thing is you have to follow the rigors of science and then follow the rigors of modeling. So you can't. It can't be an excuse for doing a shoddy job, but as long as your science is rigorous, what type of model you use should be driven by what is the application or what's the question that you want to serve. It should not be, it's probably not a good idea to have a preference for a model. The preference should be, what can I do? What model? What's the easiest or the simplest model that will get me there? Other questions? So we have covered some things. We talked a little bit about fundamentals like concentrations, some of the basic principles, comfort level. Are you all pretty comfortable with that material? You should be. It's part of your undergraduation. That's something you've learned. We talked a little bit about regulatory background. Yesterday I talked about how these groundwater regulations came about. This morning I talked a little bit about how groundwater regulations came about. So that should be fairly straightforward. Okay. What about programming? What about coding in R? We had an exercise. How many of you completed it? 1, 2. Somebody raised their hand and put their hand back. So I'm assuming that was a complete. Okay. 1, 2, 3, 4. What about the rest? What is the challenge? Or what is the limitation? Is it because we haven't tried it? Is it because we've tried and failed? Or is it because we just didn't know what you were doing? Or what is the root cause for doing it? Do you need more time? There's a bunch of things, right? So people who did it, how comfortable are you with R? What do you think? Did it work? Did it give you a nice little plume?
It is a good means compared to all other languages. It's not lengthy.
Mm-hmm.
Within a short comments we can come with the results.
Right.
And variable declaration is a very headache I'm working at a Fortran, so comparing to that, it's very easy.
Right. Okay. So I would still strongly suggest that. So should I spend some time doing R, or should we move forward? What's the?
We are doing this in a smaller area, but if we do this modeling for a bigger area, something in beginning we need some elevation data. So if I have data of 3000 points, then is it easier to do in R or something in model like in groundwater models?
looking at 3,000 points is nothing. Okay, we have done models which are like a million points, several million points an hour, and processed it. So a lot of times we run multiple R on multiple computers and break that down into multiple pieces. So what's important at the fundamental level is to understand what the logic is. The reason I want you all to write programs instead of using code is when you start learning how to model, writing a code makes you go through every step, so it kind of helps you understand what the models are doing. If we go straight to models without really writing code, what happens is you will not understand what's going on behind the scenes, and that's very important. So if it's a very complex model, there's no harm in using code, or at some point there's no harm in using code, but at least when you're learning, you need to write some so you know what that code is doing. You need to be able to say, hey, I got this output from my computer, does it make sense? Is it the right answer? So you don't develop that intuition unless you've actually written some programs. Even they may be very small. What I wrote is a very simple program, but two things that I impressed upon you was we can use a model like that to actually solve some questions in the field, and so we don't have to necessarily do a complicated model just because we can. And the second thing is just going through that exercise kind of told you, okay, this is the kind of data I need, this is the kind of equations I solve, this is how the solution looks like, this is the type of plots I can make, so how do I communicate my results. All of those are important parts of modeling. So modeling is not just writing an equation or solving a model or writing a computer code, it's everything together. So putting that together is what is the process that you have to learn. You have to go through that process. So once you get used to that process, then you will start using that process, and you will say, okay, how complex should I make this model? So if I have a larger region, I'll need obviously more data, I'll need more things. If I have 15 sources, should I do an analytical solution or should I do a numerical solution? At that point, numerical solutions start becoming a lot more easier to implement. So we start making trade-offs. Sometimes we may say I have 15 sources, but I'm going to do what one source does at each time, so I know what is the relative contribution. Then we start adding together. So there are two things that models do. One, models help you understand what's happening in your system. Two, what models help you is make predictions or make things that you help. So there are two parts to that modeling. One is what is called the predictive side, where you actually need the number to do something, either set policies or design something. That's one part. The other part is strictly evaluative, which basically means you start saying, okay, if I don't have this data, what does it mean? What are the errors associated with the model? Or if I make this model look like this, what will the output look like? So it kind of helps you develop intuition as you go through, think in abstraction, and that's what models are supposed to do. So we run models either in the predictive mode or in the evaluative mode, and a lot of times on a project we have to do both. And the more time you spend doing the model in the evaluative mode, the more understanding you'll have, and eventually the last step would be to use it in the predictive mode. So we don't have an answer yet on R. You're going to try it this weekend and we look at it on Monday, or do we want to do it now? And okay. I always tell my students that it's your class, okay? So I'm here to serve. So you have to tell me what you want, and I'll answer, okay? So the class should be driven by the students, not by the faculty, okay? If I'm telling you what you should do, it's a pretty bad class, okay? If you tell me this is what I want to do, then it's a better class, okay? So because you're in charge of your learning. If I'm telling you what to do, I'm in charge of your learning, okay? It's never a good thing, okay? If you're not going to take ownership of your own learning, then you're not learning, so you're learning because, hey, he told me to learn, that's why I'm learning, it's not coming from within. So what's our plan? What's our strategy? What do we want to do?
So we don't have much idea with this R,
Mm-hmm.
the basic.
Right.
We are lagging behind.
Yeah, that's understandable. So that's not a bad thing. So
So apart from this model, if we have 2-3 different programming for different scenario,
mm-hmm.
it will help us more to visualize. I think if these are the kind of problems.
Right, I understand, but if you there's really no easy way to learn programming. Okay, so I mean, so if you have done programming, if you have programmed in one language, learning other writing in another language is easy. Like so if you know Hindi, English is easy, right? At least you know that this is what I need to communicate. But on the other hand, if you've never spoken, like every language looks difficult. So that is a challenge that people go through. Like and that's what I'm asking. We will look at multiple programs throughout the course. I mean, that's what we want to do. But what is the comfort level? Like, where do we want to spend our time today? Do we want to spend our time doing some R? Do we want to spend some time talking about other things? What you want to do R? You don't know what you want to do? It's not a good thing. Okay, you should be confident. You should know what you want to do. Like, so what do you want to do? How many of you want to do R? Okay, and how many of you? I guess the rest of you don't want to do R. Is what it boils down to. Like right? Like so let's go and look at some R code, R functionalities, because the more comfortable you become, the easier it is. Okay, so let me look at lecture 6. Okay. So let's use something that we know and try to do a model in R. Okay, so something that we already know, and this is probably good too in terms of getting some background that's needed. So one way we do modeling is to conceptualize our systems as reactors. Okay, so what's a reactor? A place where reaction takes place. Okay, so there are multiple types of reactors. If you're environmental engineering or if you've done environmental engineering, this should be fairly known concept, right? So the first type of reactor is what's called as a completely mixed batch reactor. For short, we call it a batch reactor. What's in a batch reactor? So in a batch reactor, we have a few things. Okay, one is our volume. The solvent volume is known. Okay, it's what it is. Okay, the initial concentration is known. Okay, of your solute or your pollutant. The third thing we do is we are mixing it. Okay, so when it's completely mixed, what does it mean? Correct. So when it's completely mixed, doesn't matter where I take the sample. I can take it up in the top here, here, here. They'll all give me the same concentrations, right? The concentrations. That's what completely mixing does. And these types of models are usually done when things change over time. Okay. If you have an equilibrium reaction where the rate of reaction, forward reaction, is the same as the rate of reverse reaction, a batch reactor is a pretty useless reactor, because nothing changes. You will put the stuff, and every time you take A to B, a mole of B becomes A. Your concentration is not changing. Okay, so but if you have a system that's kinetically controlled, where your concentrations do change over time, this is a good reactor to figure out how does that concentration change over time. Okay, so wastewater treatment plants. We talked about a lot about water and wastewater. Can we use batch reactor to do wastewater treatment? Yes. Why not? So if you have a simple wastewater, and if you want to treat waste once at one shot, that's what you do. Usually in wastewater treatment plant, we use a slightly modified version of this batch reactor called a sequencing batch reactor, where we actually fill up, do the reaction, drain it, and then fill it back up again, drain it, so on and so forth. So the flow is not coming in continuously. For each block, it looks like it's a batch reactor. So we run the batch reactors in sequence where we are filling it up, we are draining it, we are filling it up, we are draining it, and between these points, we keep the reactor completely mixed so that we are reducing the concentrations. If you have very intermittent loadings in your system, some of the industrial wastewater treatment plants, or like places where you can actually store water and then get into this batch mode, you can design wastewater treatment plants to work like that. If you have a groundwater, and if you want to do ex situ groundwater treatment, that is, we want to pump the groundwater, contaminated groundwater, and treat it, we could use something like a batch process or a sequential batch process. Okay. So you know how to write mass balance for this batch reactor? So how do we write mass balances? So first thing we want to do is conceptualize our system, right? And at t equals 0, we have this. And the second thing we want to write is, and let's say the volume is V of this reactor. Okay. So what's the next thing we do? That's our first step. The second step is we need to write a mass balance equation. What is a mass balance equation? It's a statement of conservation of mass, and we say that the accumulation rate is inflow minus outflow plus or minus reactions. If you are in hydrology, we just don't write reactions, we write sources and sinks, but it's exactly the same thing. Each term is a loading term. If you have a batch reactor, there is no inflow, there is no outflow, so what we are left with is only reactions. Okay. And the accumulation is the rate of change of mass or rate of change of volume, depending on what we are tracking. If we are tracking the solute, then we are tracking mass. If we are tracking solvent, then it's the volume that we are tracking. Of course, our solvent is fixed, our volume of the reactor is not changing. So we write rate of change of again, if I express my concentration in milligrams per liter, multiply times the volume, which will give me milligrams. So rate of change of mass over time, this is my loading term, or what looks like a loading term, is equal to some sort of a reaction. If I assume first order reaction, right. So my volume is constant, so it's not going to change with time. So I can pull it out of that differential. And cancel these two volumes on both sides, right? And I'm left with this. So the assumption I made here is reaction. My solute is degrading as per the first order reaction kinetics. Then what I do, I take this limit and say if I take my delta t tends to 0, I can write this as a differential. Okay. This is a first order differential equation. You can actually separate the variables and solve it, right? And I also need to solve this, I need one initial condition. So this is my model basically. And this portion here is what we call the governing equation. And this portion here is what we call initial condition. So how do we solve this? We can separate out the variables. We can say del C over C equals minus k dt, integrate on both sides. beta, right? And at t equals 0, this term becomes 0 equals beta. So I have natural log of c equals minus kt plus of c naught, and then natural log of c minus natural log of c naught equals minus kt and if I exponentiate on both sides, right? So now let's put some numbers. Let's assume a chemical, and let's say my reactor is like 1,000 liters. So I have a 1,000-liter reactor, and my initial concentration is of some chemical is 500 milligrams per liter. Okay, and I want to remove it. Okay, and my half-life. So the time it takes for the chemical to get to half of its concentration, let's say, is 30 days. So T half is 30 days. T half is related to this K, because if it's half-life, this becomes 0.5, and I'm trying to find out what is the time associated with it. So generally, T half is equal to natural log of 2 divided by K. Okay. So because if C is 0.5 over this, I just flip on the other side and it becomes natural log of 2, right, which is equal to or I can put K equals 0.693 divided by T half. So we want to put this model in R. Since we have the analytical solution, there are a couple of things we want to do. We can solve this models like this analytically or numerically. What I did was an analytical solution because I actually used separation of variables or some mathematics to solve this equation, right? A complex model would just require me to do something much more complicated than this, but the idea is still the same. I would start with a conceptual model. I would write my mass balance equation, get a mathematical equation, and then try to solve that equation. Okay? If I want to solve it analytically, I want to say I want to do some integration. I want to get an expression that gives my state variable on one side. This is my state variable. On this side I have, where was my equation? Yeah, this is my state variable. And it's a function of other inputs that I know. Okay? So to solve this model, this is what I call my independent variable. Okay. This K and C naught are my model inputs. So I need to supply C naught and K or some form of K, and this T is an independent variable, so which means I have to assume that it's going to vary in some form or fashion. And if I do that, I can get an expression of concentration at any given time. Okay. Since it's a batch reactor, there is no component or space component associated with it, because anywhere I go, the concentration is going to be the same. So we want to put this in R. How do we do that? So we pulled out some numbers. So let's implement that in R. So to do that, or if you want to do the example that's in your book, we'll do one example. So we open R. The first thing we want to do is start by opening R, and as I said, always right click, do run as administrator, and it will tell you if you want to do. The reason for that, I'll just show you fairly quickly as to why this happens. Okay. So the R opens, you have a console. So let's first implement that analytical solution, and then what I'll do is show you how this same simple differential equation can be solved numerically using R. Okay. So to do that, I want to first write a script, new script. Let's call this batch reactor analytical solution. Okay. And as I said, something like that, so that I know what I'm, when I wrote this code. As you get into that habit, even with simpler models, because as you write longer and longer pieces of code, this practice will come in very handy, and it will not come in handy unless you religiously put what you did when you did it. It's like writing your lab notebook, right? Like you have to put a date and you have to say this is when I made the standard. Same idea. Okay. So what is the first thing I want to do is set my working directory. So this is where I want to store my results, and this is where I want to store my code. Okay. So there are a couple of ways in which you can set your working directory. One way to do it would be to go here and miscellaneous, where is it? Clear console. Well, let me just do it the way I always do it, which is to use the set working directory function. So you type in setwd, put a quote, and where do you want to save it? So I'm going to save it here, and I'm going to put a new folder and call this reactors. So I create a folder where I want to store my files. What I do is I copy that. So this is all things I'm doing in the Windows Explorer. I'm not in R. I go back to R, paste that, and as I said, either I can make this a /, because R came out of Unix. They have this legacy of using /, or the other thing you can do is put 2 backslashes. So either way, it's the same story. Okay. So one good thing about R is what's called as an interpretive language. When you have 2 types of programming languages, one are what are called interpretive languages, and one that are called compiled languages. Language like Fortran, C, C++, or what are compiled languages. Python or MATLAB, these are all part of the interpretive languages. When you have an interpretive language, what it does is the code or your program goes line by line and starts to do what is supposed to be in each line. Okay. You can make the code go backwards using loops or whatever, but generally the sequence of flow is from top to bottom. When you have a compiled language, what it does is it takes your code, turns it into a binary code, so it stores it as a binary code, and then it runs that binary code. So when you open Windows, for example, Microsoft wrote some compiled code, probably in C++, and it opens and does what it's supposed to do. The advantage of compiled languages is they're faster. The advantage of interpretive languages is you can run pieces of code and know exactly what your code is doing, so it's a lot more transparent. When I first started doing, when I first coded in 1985, we had a program called BASIC, which was an interpretive language, and it would run line by line by line. It was a great way to learn programming. Then I moved to Fortran, C, which were more compiled languages, and we were using compiled languages because the computers were not very fast. So doing something in binary was a lot easier than trying to do an interpretive language. Now the computers have become so fast or like powerful that we have kind of come back to interpretive languages. So when people use Python or R or MATLAB for their development, basically they're saying, when I'm developing the code, it's important for me to look at each step and see what's happening, and then to compile all of it into one and just run it. So if I have a very large code to run, it still makes sense to write compile programs, but if you can write a shorter piece as an interpretive language, you will know what the logic is, you will know where the errors are. It's very easy to debug. Okay. So both offer their own advantages. So what I can do is, once I write this, make sure that if you have a single quote here, it's a single quote, you can have double quotes, but if you put a double quote here, this should also be a double quote. You can't have a single quote and a double quote mixed up, but essentially they're one and the same. Okay. So we can run this, and I can copy all this. So I just click my mouse and select it, or hit Control A, and it will select the whole thing, and you'll run it. Okay. And in R, interestingly, red is good, blue is where it has, usually blue is bad, red is good. Okay. So it ran, and it came back to the console. What does this mean? What happened? Okay. So what I did was I told R, go ahead and change my working directory to this, whatever you selected. Okay. So I want to make sure that the R actually did it. Okay. To do that, what I can do is go here and put get wd, which is get me my working directory, and it shows me the same working directory that we had selected. Okay. Okay. So remember, I set the working directory to be Dropbox, yeah, and blah, 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 and I'm seeing the same thing when I put get. Now, what do you think will happen if I did not put these two quotes? Okay. So go ahead and type in. Let's go ahead and type in, and not put the quotes. Okay. And it gives you something that looks like this. Okay. And what this is telling you is the getWD is a function. Okay. It's what is called as a built-in function. It's built into R, and they have written this code probably in C or C++. Okay. That's why it has this dot internal, meaning it's part of that R package, and it's part of that internal coding that went into R. A lot of times there are functions that are written in R, and if you go and put a function without quotations, it will actually show you the code that's inside it. Okay. If it's a compiled code, it will show you something like this, but if it's written in native R, you can actually go look at that. You can look at your code. So that's why R is a fully open source software. If you write something in R, everybody and their uncle can see what you wrote. Okay. Good thing, bad thing? Usually a good thing, unless you want to keep it as a secret and make a lot of money, then it's probably a bad thing. Okay. So zoom. We'll see. How can I don't have a. Oh. So who's the computer expert who can do that? It is maximized. I have I have to go to display settings and display.
In R itself, in edit, GUI preferences are there. In edit,
What's that?
in edit option, make from edit, GUI preferences, their size is there, size 10.
That will do. Better. And then how do I get back to my display preferences? Taskbar. Okay. So we'll leave it at this, like this. So okay. So if I go back, doesn't help with this one, does it? This is still small, but so that's what it did. Okay, so the first step, I usually put step 1 and say I want to set my working directory. That was the first thing I did. What's the second thing I want to do? Functions to be used? Typically yes, but we don't have any functions here. We're going to use an exponential function that's already built into our model. So the step 2 is to read our data or input our data. Okay. So I'm going to define V, which is the volume, and I say that's 1,000 liter reactor. So put a hash and say reactor volume, and then C naught is 500. And then this is initial concentration, milligrams per liter. This would be liter. What's the next one? T half. So I'm going to put TH or T half. And T half is what? 30 days. Okay. This is half-life of the contaminant, right? And days. Okay. What else do I need? I need time. Okay. So how do I get my time? So I want to calculate this over a long period of time. Okay. So I do know that since my half-life of my contaminant is 30 days, so I'll go from like 500 to 250 in 30 days. Okay. If my contaminant standard, let's say, is 10, how long will it take for me to get to 10? So 500 to 250 is 30 days, 250 to 125 is another 30 days, 125 to 60 days is another. No? It's exponential, right? So half-life means the time it takes to go from whatever the concentration to another concentration, right? So the first, I have to go from 500 to 125 will take me 30 days. 125 to half of 125 will take me how much? Still half-life 30 days, right? It will take me an additional 30 days. From there to some other additional 30 days, that's what it's happening. Like I have to keep on adding. Let's say I want to run it for a year to see what happens. 365, okay. And what I want to do is make a sequence, and I want to go from 1 to 365 in 0.5. Okay. So what it does is it creates a sequence for me starting on day 1, okay, and to go to the value of 365, and it goes in 0.5 increment. So in the sequence there are 3 things. The first number is the starting number, second one is the last number, and the third one tells you the rate at which it goes to that sequence. Okay. I might actually make that 0.5 instead of 1. So I'm tracking. Why shouldn't I make this 0? Why can't I put 0 to 365? 0 is my initial condition. I already know what the concentration is. So really makes no sense. Okay. So I make a sequence. So let's go ahead and run this. This is, I'm going to comment this and say sequence of time, days. 2 things to keep in mind, and probably a good way to put somewhere when you do models is to write your dimensions. Okay. So our length dimension or our volume is the dimension that we want here in liters, and our time in days. Okay. So we want to make sure that we'll pick a consistent set of units and stick to those units. Usually not a good idea to stick to liters. And then our mass, what are we using? Mass is in milligrams. Okay. So but grams per meter cube is the same as milligrams per liter. So so what do we do? Step 3. Make calculations. Okay. So I can put C equals C naught times exp. Oh, before I do that, I need to convert my half-life to a rate constant. So my K is 0. Or natural log of 2 divided by T half. Okay. So the log is natural log in R. Okay. So this if I put log, it's not log to base 10, it's natural log. Okay. Will this work? I need a loop to loop through each of these values. Okay. Let's run it and see. There is no harm ever to see if it runs. Okay. So I'll just select that. I just selected step 1 and step 2, and if you notice, it just wrote all of that. So there is nothing that happened. I didn't make any calculations. The calculations really are in step 3, but I want to run step 1 and step 2 to make sure that all my data is put in correctly. Okay. If the data is not put in correctly, then obviously your calculations will not be correct. Okay. So I'm going to run, since I know my data has been put in correctly, I'm going to use my step 3, and I'm going to run it, and it didn't give me an error. Okay. And as a matter of fact, if I go to the console and put C, it'll give me all the values it got. Okay. So this is what is called as a vectorized function. Okay. So what it does is I defined a sequence. So this is a sequence of time. Okay. And when I put exp and say minus kt, Fortran and other things would throw an error and say, like, you can't do that. It's a vector. It's got a number of values. Okay. But R is vectorized, which means it takes each value in that number and makes this calculation and stores it, each value and stores it. So that's called a vector operation. Okay. A scalar operation is one where you only work on one set of values at a time. So if I write a for loop, I'm doing a scalar operation. If I do just what I did, I'm doing a vector operation. Okay? Not all functions in R are vectors. So sometimes it will throw an error and say it's not a vector operation. But R gives us functions that will help you make that function vector. Okay? So I'm going to show you that. So I made this. So if I look at my concentrations, it's showing me the concentrations. And if I look at my times, I can do the same thing. I can go back to the console and I define time as t, and it will give me all the values starting from 0.5 to 365. Okay. So what's the last step? To plot it. Okay, so that's what we want to do, plot the data. Okay. So how do we plot it? R gives us a function called plot. Okay, and in the plot, okay, so what we want to plot is C versus T. Okay, but before we do that, let's put something else. Our T, if you notice, started at 0.5. So we made all our calculations starting at 0.5. But our times 0, I know my concentration. So what I want to do is go into this C and slide my initial concentration of 500, okay, as the first value. I want to go into this time sequence and slide in 0, so that I'm plotting it starting from time 0 all the way down. Okay. How would we do that? So when you see numbers like this, okay, this is a one-dimensional array, right? It's got a one dimension. So in our lingo, we call this a vector. Okay, I can go and access each cell of a vector. Okay, but I can also insert things and delete things, or I can pull a piece of the vector based on the index of that number. Okay. What I want to do, there is a function called C which is combine. So I'm going to take my T, okay, and I'm going to use little c, which is the combine function, okay, and I want to put 0 t. What does this mean? What's that? Right. So what it's doing is the calculations always proceed in this direction. Okay. So when I start here, the value of t goes from 0.5 to 365 in 0.5 increments. So it's taking that vector and then it's adding or combining a value 0 to it. And that's what this c function does. This little c is a combined function. Okay. So what had happened, and if you notice, I wrote my concentration as capital C. What would have happened if I had made that little c? It'll still work. Only thing is, don't do it. Try and avoid it, because when you start seeing c as a function and c as a variable, your code becomes a little bit confusing. So it's always good to put a caps. If you want to use c, always put a cap c, so that it keeps it different. Okay? But it wouldn't throw an error. It still works, because it knows when you put c, anytime we put a parenthesis like this, okay, it means it's a function. The good thing about R is any function will have these parentheses or these brackets. Okay. In MATLAB, if you have ever programmed in MATLAB, you can use this to mean functions, you can use this to mean arrays, you can mean that to mean matrix. It depends on the context. So MATLAB is not a very standardized language. R, on the other hand, is a much cleaner language to write things. So when I do this and I run this code, this is the best part about interpretive languages, is I can run it, and it ran. There was nothing wrong. So I go here and put t, And if I go back and look at the first value, it has put that 0.0 for me. Okay. If you notice, I just put 0 without any decimal place, but R went and put a decimal place for me. Why? Because it's going from this side to this side. It took this t and it said, okay, this t is all in real numbers, or like in the. So it'll say, okay, I'm going to make this 0 also a real number because to be consistent, and it did that, and it went on. Okay. So then similarly, I want my capital C to be C of C naught comma C. Same logic. My C here was calculated from 0.5, but I know my initial condition, so it just adds that initial condition. So if I run this and then go back and do C, it adds that 500 to it. Okay. So just so that I remember what I'm doing, I'm going to go here and put step 4a and say insert initial conditions. Okay. Now I want to do plot. So okay. So R gives another function called plot, and plot takes the x value first, which is my t, and then it takes my y value, which is my c. Okay. And if I go and run this plot, it shows me c and t and shows me the values. By default, it will plot like points. Okay. So what was our half-life? 30 days. So my 250 approximately is like about 30 days. Right? So what's good and bad about this plot? Is this a good plot? Do you like this? How many of you like this plot? 1, 2, 3, 4, 5, 6. Okay, you guys are excused because you like it. People who don't like the plot, now tell me what don't you like about this plot? Okay, if you do any plotting, this means I don't know what this means. I don't know what that means. I don't know what the units are. Okay, so if I can make this, I don't have a legend that says what this is about. So we need to add all that. Okay, where do you do most of your plotting? Origin. Okay. MATLAB. Okay. Whatever it is, don't make plots in Excel. Okay, that is the worst place to make plots. Okay, Excel was not designed for engineers; it was made for business people. Okay, so Excel has some strange quirks. So as long as you don't make a plot in R, and this is where R really shines, is you can make really pretty plots in R. Okay, but to do that, you have to tell R every little piece of information. Like so, if you use something with a user interface like Origin or something, it'll say, okay, I'm going to put my, I'm going to put all the axes and stuff for you, and makes you lazy. Downside is here, you can't do that. You'll have to go and tell that. So the way you tell it is, first thing is, I want my label, X label. So it's X lab is time in days. Okay. And then Y lab equals so if I do this and run, now we put time in days, put concentration. Okay. You can also put a title and say put me. How many of you like that black color? Okay, so I'm going to change it. Now, let's say I'm going to go back to black. Let's say what I also do usually is put grid, and it adds a little gray grid on top of it, makes the graph look a little bit more scientific than anything else. So if you have only one curve, a legend is usually not necessary, because you know what, that there's only one curve. If you have more than one curve, you do want to put a legend. How do you put a legend? So if you don't know, the best place to do is to just go and say help legend, and it will show me that there is actually a legend function. Okay. So R has a built-in code, so if you go put help and look for a function, it will look. The other great place to look for stuff is just Google and say, how do I do this? And you will actually get a lot of code that people will tell you this is how you do it. So that's the best part about R, is there's a lot of help. So if you do take that help, which you will, be sure to give back some as well. Like, so if somebody comes and say, how do I do this in R? Don't keep the knowledge to yourself, share it freely. Like, that's the idea of open source. Okay. So what it basically tells is, I can put a legend. First, I have to tell where I want that legend, so that will be my X and Y. And then I have to actually put a legend, and the legend says, like, if I go here, it says what needs to appear in the legend, like, what is that I want to put in the legend. And then I have to say whether I have what color, so what is the colors of that graph, line type, line width, PCH is the point scale. So I can specify every little thing, and I can put a legend to it. Okay. So if I go to R, go back to my model, this is, okay. So in the plot, let me go here and put comma PCH equals, pick a number 10. Okay. Let's see what it does. So it changed it to a diamond, open diamond. Like, it went from being a circle to an open diamond. So if I want to put a legend now, what I can do is I can say I want a legend. Okay. And let's say I want the legend somewhere in this area. So my y-axis is 400, my x-axis is 200. So 200 comma 400 comma legend equals, there is only one, concentration, okay, and then PCH equals 10, call equals black. And it shows me, put a little box, put the point, says what it is. Okay. So that shows me what the legend is. Okay. You can by default put it top left, top right, all that stuff. I usually don't like my legends to be sticking to the box, because it just looks odd. but it kind of gives, R gives you control where you want to put it. If you're making multiple plots, using top left or top right makes sense because everything is nicely aligned to one location. But if you're making single plots like I just did, play with it a little bit and move your legend to where it looks pretty. So spend some time. So this is one thing, you have to spend some time visualizing this data and presenting this data. It's very, very important to present model results. Let's say my concentration was 10 milligrams per liter, okay, was my standard. So what I'm going to do is I want to plot a line wherever the 10 milligrams per liter is and put a line through it so that I know at approximately what time it became, it crosses that threshold, right? So to do that, there is a function called abline, okay, and what do I want? I want a straight line, okay, a vertical line or a horizontal line? Horizontal line, and at what value? 10. I want this call to be red, okay, and I want my line width to be 2, which means I want to draw a slightly thicker line. Okay. So it draws me a line, and approximately it tells me where this is crossing. Okay. So if my standard was to be 10 and I were to use this reactor, I would have to run it for about 150 days or so before I can discharge that value. Okay. So for half a year, that reactor will be running before I can make any discharges from it, okay, because of the half-life. Okay. Now, if I want to exactly know when that concentration 10 is met, okay, this graph gives me an approximate value, right? This is where it is. If I want to know, what I want to do is I want to interpolate on this graph. I want to say, okay, I have these numbers, interpolate and tell me what time is this 10 happening. Okay. So to do that, so step 5, find out time to compliance. Okay. Compliance is when you meet the standard, and then you say C standard is 10. Okay. Then what I do is I say time to compliance TTC, okay, is, I want to approx, okay, I want to take my C and I want to take my T, okay. So I'm taking C versus T and I want to interpolate, and the value I want to interpolate to is the C standard. Okay. And if you do this and run this, okay, C standard is, it's saying it didn't find C standard. The reason it says it didn't find C standard is because I never loaded that into the memory. So I have to run these two lines to make sure that first I get the C standard in. Okay. Now it ran, and if I go back to the console and put TTC, it's saying my X value or that standard is 10, and then the Y value is 169. So it takes about 170 days before it hits that 10. Okay. And if you notice this, there is a $X, $Y. Okay. So R has got two forms, but for most things, if there are multiple values, if there are more than one value, this is called a list. You can go and get an element out by simply putting dollar and that element. Okay. So this TTC is an object that has two elements in it. One is X, one is Y, and they are written in different slots. If I put $X, I have access to that slot. X slot. And if I put $y, I have access to that Y slot. So I really don't want my X because I know it's 10. So all I want is Y. So what I do is I just go here and make it $y. So it only writes that $y instead of writing the whole thing. Then it's just writing me. So if I do this and then run TTC, it's only giving me one value, which is the value that I want. Okay. So we have this graph. Okay. What do you do with this graph? We save it. Okay. R has a couple of options again, like in anything in R, you will get multiple options, okay, generally speaking. Okay. And that confuses students a lot because they're like, why do I need to know 4 ways to do the same thing? Like, can't I do just one way and be done with it? The reason for that is R is open source. Multiple people are contributing to it, so multiple people write different ways to do it. Okay. So you have to pick what works for you. Okay. One of the quick and dirty ways to save it is to just go to this and say File, and then Save As, and it gives you a bunch of options to save this either as a JPEG, TIFF, BMP, PDF, so on and so forth. Okay. So what is a good format to save it? Okay. So can anyone tell me what JPEG is? Correct. So it is, all of these are image files, or like these are image standards. Like this is how we store image files. Okay. JPEG is basically, as he said, is a compresses it. So what it does is it says, okay, I have a picture. There are all these dots. Okay, I'm going to sample these dots once every 3 dots or 4 dots, and then so I can get a fairly crude image or a very fine image. Okay. The worst format to make pictures is what? What's that? Paint is a software, like you can. If you want to put a picture on your website, you should probably use JPEG or GIF. Okay, GIF is the graphical image format, and then because those two have very low resolution. Okay, GIF has a really bad resolution. Like JPEG, you can control the resolution a little bit, but it's still bad. The advantage of that is the file sizes are small. Okay. TIFF is the tagged image file format. TIFF does pixel by pixel by pixel by pixel by pixel. So you can actually specify what is that pixel density that you want. So you can make a very, very high quality image out of TIFF. Okay. The downside is TIFF files are very large. Okay. And if you are publishing, you all want to publish our papers, right? Most journals will require you to do a TIFF, send it as a TIFF file, okay, because they want it to be a high resolution. Okay. So what R can do for you is it can actually write a TIFF file. Okay. The crudest way is to go here and use this TIFF, okay, but I wouldn't recommend you doing this because it doesn't give you the resolution at which it saves. Okay. If I have a computer screen, what is the resolution on a computer screen? Okay, so the way we measure resolution is how many dots per inch. Okay, so how many pixels do we have per inch of whatever our media is? Okay, by default it's 92. Okay, so most journals, if you read, will say I want 300, 350, 450, whatever you want, like So JPEGs, TIFFs, GIF I think does like 76 by default. So on a screen it will look just fine because the resolution you're looking at is only 92. But if you print it, it will look pretty bad. It looks pixelated. It doesn't look very good. Okay, so you can do TIFFs at multiple file formats, and the way to do it is to actually use the TIFF command. So I'm going to go here and say help, and it shows me all the different file formats in which I can do. So the PNG and TIFF are really the best formats. JPEG is a file. You can actually control the resolution of JPEG. BMP is, if you try to take this to a Mac or to a Linux machine, BMPs don't work. It's a native Windows format. As long as you're in the Windows, you're fine. Okay, but it gives me a lot of different things I can do with TIFF. The first thing it tells me is I can put a file name and put .tiff. It'll store that, and then I can specify the width and the height, and I can make a picture of a certain height and a certain width, and instead of using pixels, I can also use inches. Okay, so that I have pixels, you don't know how many pixels you really have. Inches, you know exactly what the size is. Okay, you can also set this res. Here it's NA by default, but if you make that 450, you're going to get a 450 resolution, 450 DPI picture. Like, and if you put 300, you'll get a 300 DPI picture. Okay, and so let's go ahead and make a TIFF file of what we just made. Go back to my model and say okay, and then step 6. Make a TIFF file of my output, okay. And so the is TIFF, right? So I want my function to be TIFF. What else? The good news about R is when we do the help file, if you usually scroll down, it'll show you what this help file is. Okay, and one of the things when you make a TIFF file is, so if I don't make, before I go to the TIFF file, let me tell you this. Okay, so if I look here, right, where is my image? This is my image. Okay, so it created something called a graphic device 2. This window is named graphic device 2, and then once it opened that graphic device 2, it wrote this, or it plotted this picture. Okay. So what I want to do is, instead of writing it to this graphic device 2, I want to write it to a TIFF file. Okay. So I'm not really copying this file, this image here, but what I'm doing is I'm saying, open a TIFF file for me, put this image, and then close the TIFF file. Okay. That's what I'm trying to do. I'm not trying to do is, I'm not saying take this image that's out there and copy it, because this image by default is 96 dpi. That's all it has. Okay. If I copy it, I'll only get a 96 dpi image. I'm not going to get a 350 dpi image. Okay. So what I want to do is, I want to open a TIFF file first thing. So I have to say, if I open a TIFF file, I'm going to say open a file with this name. Okay. Then I'm going to say make this plot in that TIFF file, and then close that TIFF file. So that's the logic that I have to follow. So if I want to do that, I have to go and say, I'll go here, because this is the plot I want to make. Okay. So if you want it, you can copy and paste, or so I put TIFF. Okay. What is the name of the file I want it? Batch.tif. Remember, it just takes .tif. If you go back to the help file, and if you notice, TIFF file name sum.tiff, right? Then I can give the width, height, and the resolution. Okay. So I'll go back, and what is my width? So let's say I want to make about 5-inch picture. Height is, let's say, 5 inches. Units equals inches. If you don't put it by default, it takes pixels. So 5 pixels by 5 pixels is a very, very, very tiny picture. You won't see anything out of it, okay? And then res equals 450. Okay. So what this does, what this file does, is what this statement does is it opens a TIFF file, calls it batch.tiff. Okay. Where is it opening the TIFF file? It's opening it in the working directory that you have. Okay. That's where it opens it. It opens the TIFF file, and then it makes the plot. Okay. And what do we know about computers? And then it goes and does all this stuff. Okay. What do we know about computers? It's opened the file because you told it to open the file. It made a plot because you told it to make a plot. And it says, okay, add a title. It'll add a title. And then it'll say, okay, I'll add a grid, I'll add a legend, I'll do all this thing. Now what? So you have to close the TIFF file before you close it. But if you don't tell the computer close the TIFF file, it won't close it. It'll keep it open for you because you never told it. You know, it's what it is. So unless we get into some intelligent computing at some point, right now it's just open. Okay. So what we want to do is, remember, it's writing it onto some device. Okay. So it's a graphics device. A TIFF is a graphics device. It's just like this, except it's got a very high resolution, and it's not showing. So I want to close that device before I do anything. So I put dev.off, and that function basically closes that TIFF file. Okay. So this is to close the TIFF file. Okay. And so if I just run this portion, it says okay, it closes. It usually writes window equals 2, and if I go back to my set working directory, it's got me a TIFF image. And there, that's what the image looks like. Okay. What I typically do is I first make my picture on the console, okay, to see and play with it till I get it to the way I want it to be. Then I go and insert the TIFF and dev.off up on the top. Okay. And if I want to, since I don't want to be writing, if I want to rerun the code, I don't want it to be writing to the TIFF, I want it to be writing it to the console. So what I do is I go and hash this out once my picture is made. Okay. So next time if I want to make the picture, I just remove those hashes and then it will write me the TIFF file. But if I have that TIFF and dev.off, it will keep on trying to write the file. If the file is already written, sometimes it throws an error and says like, you already have that file. Like, So one thing we'll see is that file, which is a very, very, which has got very little data. There's a lot of empty space here, right? Okay. But how big is that file? Okay. It was like a big file, fairly large file for what it is. Okay. So we got this model to work, and we made a plot, and we learned how to make whatchamacallit, and store it. Okay. Now this was a simple differential equation, so we were able to separate out the variables and solve it. What if that equation was, if I want to solve this numerically, how would I solve it? How would I solve that differential equation if I want to solve it numerically? Any ideas? Right. I don't want to do analytical solution. Right. So you can use finite difference, finite element. If you have a differential equation, what we say is my t is 0, right? And this is my time dimension. Okay. So when we solve it numerically, what we are trying to do is, the key in mathematics always is, if you have an equation, our governing equation was dc dt equals minus kc. That was our equation, subject to some initial condition. The initial condition is c is equal to c naught at t equals 0, right? So this is a differential equation. The key in mathematics or in mathematical modeling is, if you have an equation and you don't know how to solve it, what do? I have some equation and I don't know how to solve it. Okay? So the golden rule in mathematics is, if you don't know how to solve an equation, you should make that equation look like another equation that you can solve. If you can do that, then you will solve that equation, you have solved your problem. So the trick in mathematics is, I have equation A, I don't know how to solve it, but if I can make it look like equation B, and I know how to solve equation B, my life is solved. I can just solve equation B and then transform it back to equation A. So the entire mathematics is kind of based on that idea. If you have this, what numerical methods do is, they say, you have a differential equation. If you don't know how to solve a differential equation, turn that into a set of algebraic equations. If you can solve for that algebraic equation, then, which are simpler to solve, they serve as an approximation for your differential equation. So we start at time t equals 0, my c naught, that's known, right? And what I do is, I break that continuous differential equation into a set of times. Okay? T equals 1, t equals 2, okay. So instead of making calculations over this entire continuum, I just make calculations at these discrete points. Okay. And what I do is, I say, okay, my dc dt is my differential equation. I'm going to write it approximately as c of t 1 minus c of t divided by delta t. Okay, this would be the very simplest form of solving this. The time between two intervals is my delta t. Okay. And I can just say generically, this is t plus 1, this would be t, this would be t minus 1. Okay. So for my t equals 0, I know my value, and I can write that c, and my equation that I want to solve is equal to minus kc. Now, what c do I put there, t plus 1 or t? Right. So if I put t, then the only unknown here is this t plus 1. There's only one equation, which is my only unknown. Okay. In this, I can also put t plus 1, and I'm still have to solve for t plus 1. If this happens to be a fairly simple equation, so if I put t plus 1 or t, it doesn't really matter. But if this is like some complicated equation, if I make it t plus 1, I'll have to solve some nonlinear equation, algebraic equation. So a lot of times it's just easier to put t. And is it a good approximation? This is okay as long as my delta t is small. As my delta t tends to 0, okay, my change is not that much, and I'm okay with it. Okay. So I'll write c of t plus 1 minus c of t over delta t is equal to minus kc of t, and then so c of t plus 1 is approximately equal to minus k ct times delta t plus C of t. Right. So first my t equals 0. So at t equals 0, C of t plus 1 will be C1 at time 1, and that's approximately equals to minus k C naught delta t plus C naught. Okay. I know my C naught because I know my initial condition, what I put into my batch reactor. I know my k, I know my delta t, so I can calculate my C1, and my at t equals 1, C of 2 is approximately equal to Kc1 delta t plus C1. I just calculated my first equation, so I can just put it into my second equation and I can march forward. So this is what is called as an IVP, or an initial value problem. Okay, you start off with some initial value and you march forward. Okay, and what we are doing is we are approximating the curve. So we know our curve is exponential. What we are saying is it is made up of piecewise linear segments. So we have kind of taken a differential equation, converted into an algebraic equation or a set of algebraic equations, not just one, because at each time we have one algebraic equation and we are solving for several algebraic equations at the same time. And so we just took an equation that's harder to solve, turned it into something simpler. This would be what is, this simple method is what's called as the Euler's method. Okay. And if I want to do is, if I say, okay, instead of taking these 2 points and taking, a linear, assuming a linear relationship between that, I'm going to first do this, calculate my new estimate, and then go back and take a midpoint and do it again. Okay, so you get what are called a family of RK methods or Runge-Kutta methods. That depends on how many types you're going to further chop, like, so there are many ways. Okay, there are some better methods. If you have a linear equation, it really doesn't matter. But if you have a highly nonlinear or transient problems, especially if you have Monod kinetics, for example. What's Monod kinetics? So it's an autocatalytic reaction, like, so your reaction rate depends on what concentration you have. If you have very high concentrations, it looks like a zero order reaction. If you have very low concentration rate, it looks like first order reaction. But in the middle, it's got some mixed order reaction into it. Like, so that's what Monod does, and it's a highly nonlinear reaction as opposed to a linear reaction. So what happens is, for certain types of values, this curve is not smooth. The derivative just does something like that. Okay, so you have to. If I were to do Euler's method, I have to finely chop, and it takes a lot of calculations. So what these autocorrection methods do is they kind of go and look for those transients, and then they say, if I have a transient, I'll chop it and make it finer. If the curve is smoother, I'm going to run it at a higher time step so that you get the benefit of both worlds. Like, so R by itself doesn't have a built-in differential equation. It doesn't come with a differential equation solver. You can't go and solve. You can't go to native R that we just downloaded and say solve me a differential equation. But R comes with a package called dsolve. Okay, and dsolve gives you a whole bunch of tools that you can use to solve differential equations. So to do a lot of R's functionalities are packaged separately. We have to go download the package that we want and access that functionality. So what we'll do is solve the same problem. So we'll go ahead and save this and call this batch analytical. We'll save it. Okay. Now, what we want to do next is I'm going to close this graph, and either you can keep the same. You can keep this open or you can close it. It's up to you. So what we'll do is we will first download the package that we want. Okay. So if you don't know which package to use, generally it's good to go to Google and say ODE, because we are solving an ODE, ordinary differential equation. You guys can still see on this, right? So and it shows me that I can use this package dsolve. Okay, so I have to download package dsolve. So the way we do that is go back to R. Okay. Go to packages and do install packages. And first it will ask you where do you want to get this. Pick the one that's closest to you. I usually go pick USA Texas 1. That's because that was usually what's closest to me, but I'm sure there's one in India, right? So it goes and makes a connection to that mirror, so you need to have internet access when you do this, and then it lists all the packages I have that I can pick from. Okay, so one way to do it is to go and look for that dsolve, go back and see that it's written with lowercase d, e, and capital S. So this is dA, dB, dC, dd. So we get into decode, default, the demi, so there is that dsolve. So I can select that, okay, and say OK. So what it does is it pulls that package from that web server, puts it onto your computer. If you go and if you had run R as an administrator, that package is available to every user on your laptop, okay, or your computer. If you had run R with just normally not as an administrator, it will still install it, but only it will be available for you. It won't be available for somebody else. So if you log on with another account, you won't see that, like, and it won't be accessible to them because it will write it in your portion of the drive. Okay. So all this install.packages, I mean, so it does is it put dsolve on my computer. It has not really loaded it. Okay. So the first thing I want to do is I'm going to open a new script. Okay. And this is solving batch reactor kinetics with dsolve. Okay. What's the next thing I need to put here? By whatever. And on whatever date. So here my step 1 would be to load my library. Okay. So to do that, all we say is library desolve. Okay. Make sure you keep R is case sensitive, so make sure that you have the capitals correct. Okay. And make sure that you have installed this package before you call it in the library. Okay. If the package is not installed, that code will not run. That line, it will say okay, and it will throw an error, and it will say, I don't know what you're asking for, like, and I don't have it. Okay. If I have this and I just run this portion, and it did put my desolve here. Okay. So the next thing I want to do is put my working directory. Because I haven't closed R since I last set my working directory, it will still be in the same working directory. Like, and I haven't really changed it, but I'll just go copy it just so that this code is complete. Okay. So, okay. Then what's my step 3? Input variables. So, inputs. Okay. So, I'm going to take these two, okay, put it there. Okay. What else do I need to put in? I have my t half, right? Okay. I'm going to go here and make that calculation of k. So I'm going to change this and say okay. Okay. So it made this calculation. Now what I want to do is find a way to solve my differential equation. I know that when I did my Google search, it told me this is how you can use this package desolve to solve my initial value problems. So how do I go about solving it? I can go and open this. So if you go to CRAN, which is where your R is, every package comes with documentation, and R has these very strict rules on how you need to put your documentation. Okay. So it gives me a lot of different functions. You know how to solve one-dimensional ODEs, two-dimensional ODEs, blah blah blah. There is a function called LSODA, and so LSODA solves both stiff and non-stiff systems. Okay. So the stiff systems are like the Monod kinetics I was talking about, where you have this sudden transients which makes the equation very difficult to solve. Okay. Stiff equations, broadly are defined as equations that if you take from the differential equation to an algebraic equation, there are certain portions where the equation is very difficult to solve. Okay. And what it tells me is it tells me what this LSODA function looks like. The first thing LSODA wants is a y value, and this is the initial value of the ODE. Okay. So if I call LSODA, first thing I need to give is my C naught. Okay. The second thing is times at which explicit estimates of y are dissolved. Okay. The first value in times must be the initial time. So I always have to have my time to start at 0, because that's where I'm starting it. And then it is telling me where all do you want to make the calculation. Okay. Then the second thing is func. Okay. and this is the function, okay, that is used to define the derivative. Okay. So, this function is the right hand side part of our equation, of our differential equation. So, if you have differential equation, what you need to do is so our differential equation in this case is dc dt equals minus kc, right? And our initial condition is, so if you have an equation, you should always bring it to the form where on the left hand side you only have dc dt. Okay? By the way, in LSOTA you can solve system of differential equations. So, if you had 2 or 3 chemical compounds, one dependent on another, you can solve that using LSOTA. But all the terms on the left hand side should be dc dt. So, if I had a dc dt, for example, in some equation, I have to divide throughout by a to get rid of that a. Okay. So, my dc dt equals minus kc. So, the function is something that defines this. Okay. And they also have some rules on how that function should be. It says that it must be defined such that the first value is your time, second value is your concentration, and then any other parameters that go into it. Okay. So LSOTA, the first value of the LSOTA is your initial condition, right? And the second value is the times, and the third value is your function. Okay. And then the fourth value is your parameters. Okay. Then the function itself must be written so that the first is t, next is y, and then any other parameters. It should be in that order. Okay. So if you want to go down, it'll show you an example of what the parameters are, the sequence of times where we want to do these values, and it gives me the LSOTA, and it says the first value is the x start, which is my initial conditions here. This is solving for actually 3 equations, like, you know, so this is my initial conditions. The times, as you notice, somewhere they define times. So this is the starting values. Times was defined somewhere. Yeah, times was defined as the sequence. Okay. And look at this equation. The first thing is t, next thing is x, and the other things are parameters. And it's writing these 3 different equations, ds, dp, dc, which are my 3 equations. Okay. And notice that some of them don't have time in it, yet this function will have a time there. So, we'll minimize that, go here, and usually I write my functions on the very top, and I'll tell you why. And then here, this is function for ODE that I want to solve. Okay. So, we'll call it dc dt. That's what I want to solve, is a function. Okay. And the function always should have time as my first variable, second should be c, third should be params. Okay. So, I have 2 params, k and v are the 2 things are my model inputs. So, what I am going to do is I am going to say k is the first value is the k, my v, no, c naught, sorry. Okay. And I'm going to say whatever the value of ODE is minus k times c. Okay. Actually, c naught is my initial condition, so I don't really need this. And since I have only one param, I'm just going to call this k. Okay. And the return basically returns the function value. So when you put a function, what R does is it goes and creates a memory for that function, some space, and it will start putting all the values associated with it in that space. Okay. Now your main program is sitting somewhere here. So what the return does is it takes the value here and puts it back here. Okay. So that's all it's doing. Okay. So if I run this function, it will run, but it doesn't do anything. Okay. So which is fine, we'll just leave it there. And then I'm going to go here and then say step 5. So I have to define time, right? What's my time? So I'm going to go and define my time here. T is sequence. I'll start at 0 because I always have to, and I want to go to again 365 days at a time step of 0.5. Okay. So at a half day interval, I'm making my calculations. Okay. So I'm just going to run all this and just written all of that. Okay. Now I want to somehow keep my concentration, right? So my 5th step is okay. For this, I'm going to put my C and I'm going to call LSODA, okay, because that's the equation solver. And if I go back and look at my equation solver, the first value should be my initial condition, second value should be my time, third value should be my function, fourth value should be my parameters. Okay. So the first value is C naught, second value is what? Time, so that's T for me. Third value is my function. My function I wrote was dc dt. Last value is k, which is my parameter. Okay. So this dc dt should already be loaded in the memory before you do it, which is why I put it in the top, because it's an interpretive program. If I run this code at once, everything on the top gets run. Okay. So I've already put the function in, I've already ran till this step, so I'm going to go and run this and see what happens. So function must return a list. Okay. So what we need to do is go back to R and change our function. Instead of just saying okay, return OD, I'm going to call it list OD. Okay. So we rerun the function Okay. Everything else is run, so let's try and run this again. It ran it. Okay. Now if I go put C, it's giving me two things. That's why it wants it as a list. The first number is my time. So if I go all the way, my first number is my time, and my second number is the first differential equation that I solve, which is my dc dt, and it starts off with 590, 494, 488. Okay. So if you follow the rules, the two rules that you have to keep in mind is dc dt, this is the function that I want to solve, the differential equation that I want to solve. That function should always have time as the first variable, which is your independent variable. If you're solving an ODE, you only have one independent variable, either x or t. The second should be your state variable. You can have more than one because you could be solving more than one ODE. Okay. And then the parameters associated. Okay. And the function has usually the right hand side, of your differential equation. You should bring down your differential equation to look like dc dt equals f of x t, and then that f of x t is what you write here. Okay. And then when you return it, you have to always return it as a list. The reason you want to return it as a list is list contains more than one object, and what it does is by default it will return the time and it will return the concentrations for you. So even though your function doesn't have a time, it actually takes the time because it has to take that previous time step value and make the calculation at the next time step. And when you call LSODA, you need to make sure that the first value is always the initial condition, the second value is the times at which you want the calculations, the third value is the function, and the fourth value is the parameters. So if you do give this values in this sequence, it will run. So now how do I pull out just the time? Okay. Now I want to plot this, right? And just to make things a little bit, I'm going to call it CNUM, just to means it's a numerical solution. And then I'm going to run that as a numerical solution. I'm also going to step 6 because I want to check to make sure that the numerical solution is coming out correctly. So C analytical, okay, C ana is C naught times exp minus k times t. Okay. Let it run. Okay. Now what I want to do is I want to go and plot these two onto a graph, okay. But keep in mind my Cn, if I go and put Cana, it is just a vector, okay. Whereas if I go and put C, what did I call it, num, it's a frame, so it's got a list, it's got two columns to it, okay. If I go and put, the last step would be, okay, my t, so I plot my t because that's my x-axis, and my numerical, so you want to plot the analytical or the numerical? Both? Okay. When I do plot, right, it always plots me a points, like, so let's plot the analytical solution first, okay. Sienna. If I do this, I can't because it's got 2 columns, so it will plot me 2 columns. What I really want is just the second column because that's where the concentrations are. So what I do is I say use these square brackets and say just get me the second columns. So the first is the rows, the second one is the columns. If I leave the rows blank, it means I want all rows of that column. If I leave 1 comma and blank, it will get me all columns of that first row. Okay? So, and R follows row column convention. There are some programming languages that use column row convention, most notably Fortran. Okay. So, but C, C++, most modern languages use the row column convention. Fortran does column row convention because in Fortran X is columns, Y is rows. So when we wrote models, columns came first because X came first and then Y came second. So, so I want to plot this. My X lab is time, and this is in days, and my Y lab is concentration, and this is in milligrams per liter. Okay. And then call equals what color? Blue. Okay, we'll use blue and red. Okay. So if you have a code and you want to break the code into 2 lines, you can do it, but you should always break your code after a comma. If you cannot, if you break it before a comma, it will give you an error. It will think that the line has ended. Okay. So what happened? Why did it not plot? Oh, Sienna is not what I want. Sinum is what I want here. Okay. And I get my nice little blue curve. Now, if I want to plot an extra, I use points, okay, because I want to plot points. I want to plot T, Sienna, okay. Do I need to give X lab, Y lab? No, they're already given, so there's really no need for me to do anything. But call equals red, and I'm going to make PCH equals 12. I'm going to add a PCH here too, so that way. Okay. What happened to the blue? It didn't. What's that? It overlaps, okay. As a matter of fact, if I want to check that, what I can do is I can do Sienna minus Sinum, comma 2, and all these numbers are really, really small, 10 to the power minus 7, 10 to the power minus 8. For all practical purposes, they are 0. Okay. Since this is a simple model, our analytical solution and numerical solution give you very, very similar results. Okay. If you have some more complicated models, chances are you will see some regions where your analytical solution will not match your numerical solution, or numerical solution will not match your analytical solution. Okay. But this process, when we write a model, numerical model, is we have to always go back and check with the numerical solution. Okay. If we have to simplify the model to check with the numerical solution, to check with the analytical solution, to make sure that our code is actually working properly. Okay. So it uses by default uses a mixed order Runge-Kutta method, 5th order slash fourth order, depending on the nonlinearity of your problem, and then it solves for you. So the latest and greatest ODE method is what's called the Brent method, and it actually does this mixed. It'll solve it as either a fourth order or a fifth order Runge-Kutta, depending on what your nonlinearities are in the problem, and that's what LSODA does. LSODA is also available on MATLAB. It's the same engine that runs on MATLAB. They call it ODE. Here it's called LSODA, but it's virtually the same engine. So one's free, one's expensive. That's the only difference. Like, you know, so if I want to put a legend, how do I put a legend? So I'm going to again put a legend, and I have to first decide where that legend needs to go. I'm going to try top right, okay, and then now I have two things in that legend, right? So I want to put my legend, okay. So what are the two things that I have? First is an analytical, second is a numerical. Okay. Oops. So those are the two things. Okay. What's my PCH for my analytical? It's 12, and I'm going to rerun this. Make it 10. Okay, that way 12 and 10. Then what is the color? The first one is analytical, so that's red, comma blue. Ran it, puts it in the top right. One's red, one's blue, one's analytical, one's numerical. You really cannot see it because they're right sitting on top of each other. And to make it pretty, I will put a grid on it. And then I can put a title if I want. As a general rule, if you are making scientific computing, if you want to publish to journal papers, don't put titles, because you will have a caption in the bottom that says figure XXX. So you write it there anyway. So if you put a title, use that title to say something else, not just that. So now what we'll do is, let's say I want to, one of the things that R can do is you can also put multiple plots. Okay. You can arrange them as 2 by 2s, 4 by 4s, 3 by 3s, whatever. Okay. And if you try doing this in Excel, it's pretty bad, because you have to manually put them in one size. So R has, by using a couple of commands, you can actually lay them out. Okay. So what I want to do is, I'm just going to replot this in a multiple columns. So the command is par mf row equals how many? Let's say I want a 2 by 2, okay, 2 rows and 2 columns, and I'm going to first run it. This is something you have to run. So I'm partitioning my area into 2 rows and 2 columns. Okay. Then I'm going to run this. Now it only puts it in one portion. Okay. If I were to run it again, don't run that par mf row, but plots like this are what you typically put in a journal article, like, if you had 4 different kinetic experiments or 4 different simulations, you can start putting there. You can put a title and say k equals 0.5, k equals 1, k equals 2, and you can see what different rates do. Like, so R is, when it comes to visualization of data, R really shines. Like, that's one of the advantages of R is it'll give you much better plots than MATLAB. And the second advantage you have with R is a very consistent language. If I want to use a function, you'll always see these brackets, like, regular brackets. If I want to access a matrix, you will always see these curly brackets. In MATLAB, they both are brackets, and it creates quite a confusion sometimes to say, is this really a function or is this really So, do we want to do another one, or what's the time? 5:15. What about another reactor? So this one was easy. What about a continuous flow stirred tank reactor? What do we know about continuous flow stirred tank reactor? It has inflow and outflow. Can the inflow and outflow vary? So what happens? So what I'll do is, since we are breaking for the weekend, I'll give you an assignment. The assignment would be to do a mass balance for a continuous flow stirred tank reactor with some caveats. Okay. What is the, yeah. Okay. What I want to do, the problem I want to solve is, I have a continuous flow stirred tank reactor. Right. And what is the characteristic of a continuous flow stirred tank reactor? It is completely mixed. Some people call it completely mixed flow reactor. Some people call it CFSTR. Some people call it whatever you want to call it, you can call it, but it essentially means the same. There is some inflow and some outflow. Okay. The concentration in the reactor is the same as the concentration in the outflow. Because it's completely mixed, if I take a sample anywhere in the reactor, it's going to give me the same value, right? And it also means that it is the same volume water that's going out. Okay. So we'll start off, the kicker, or that what you need to kind of play with, is our reactor starts off at 10 liters at time t equals 0. And just to be SI, we'll make it 10 meter cubed at t equals 0, and goes to t equals 10 days. Okay. And it stays at 1000 liters throughout. Okay. How are you going to do it? And then the concentration, influent concentration C, okay, is, let's say, 10 grams per meter cubed at T equals 0, okay, and it goes to 100 grams per meter cubed at T equals 10 days, and it stays at that concentration throughout. So, I'll make it a little bit easier for you. Okay. Instead of giving you the volume changing, I'm going to change the flow rate. Your Q in is, let's say, 1 meter cubed, or even let's say per day, or let's make it 100, and goes to 500 cubic meters per day. So, your flow into that reactor, okay, is starts off at 100 meter cube per day, and then goes to 500 meter cube per day on day 10. So, since we don't know, since I haven't given you anything, you can just assume it linearly increases over time
After 10 days.
for the first 10 days. So, at time 0, my flow is 100 meter cube per day. Okay. So, this is 100, okay, and it goes up and becomes 500 this is 500 meters per day, okay, and then it stays 500 meters per day, meter cube per day, sorry. Okay. This is day 10. Okay. Your concentration similarly starts off at 10 grams per cc, and becomes 100 grams per cc for at 10 days, okay, and then let's say, so between 10 days to 100 days, it stays 100 grams per cc, and then it goes back to 10 at 110 days. So, your flow is going up, staying. What's that?
After 10 days.
Where is it? So, Q in is 100 meter cube per day, okay, and your Q out, your Q in becomes 500 meter cube per day after 10 days, and it stays 500 afterwards. Okay. Your concentration goes from 10 to 100, so over 10-day period, and from 10th day to 100th day it stays constant at that 100, and then from 100 to 110 it drops back to 10 and then stays at 10 throughout. So, your reaction rate, again, let's assume it's first order, okay, and I'll give you, take the same half life, T half, is, let's say, 20 days. Okay. And your evaporation rate, your water evaporates from your reactor because it's just staying outside. Okay. And let's assume you lose about 1 meter cube per day. Every day is a loss of the reactor. So we have a reactor. And let's say your discharge, okay, your Q out is okay, let's change this number. So let's make this 125. Life is easy. Otherwise, you'll end up with a very big reactor. So basically, it's like an equalization basin. You're getting flows that are not constant, but what you want to do is you will discharge at an equal rate. Okay. So you're starting off with a flow of 100 meter cube per day, ramp it up, goes to 125 meter cube per day and kind of stays there. Okay. The concentrations do some fluctuations. Okay. These are some seasonal variation to that concentration. Kind of goes up, stays same, goes down. Okay. And your half-life is the same. It's the 20-day half-life. And your outflow is always 75 meter cube per day from the reactor. Okay. You're only bleeding out 75 meter cube per day. Okay. So and your Q in is a function of time. Okay. And your C in is a function of time. Okay. And other parameters are, yeah.
It is waiting outside. If it is few minutes late, then we can continue. Otherwise, after that, we can continue.
Just a few minutes. Yeah, 5 minutes. Come. Okay. Yeah. Everybody clear about the reactor, the way the reactor is set up? Okay. So apparently there is tea outside. So why don't you have a cup of tea and think about this problem? Okay. And then after the tea, we'll come back and see who can write a mass balance equation for this, who can write equations for this. Okay. We've all seen textbook problems where CFSTR equations are there, right? They will not work for this problem. Okay. So I want one volunteer before we go on a tea break, who's going to come and solve this problem for me. Anybody? Are the ladies up to the challenge? Or will you shame the guys into saying that you are smart and they're the better half? Or
Only mass balance equation or full solution is required?
no, we're going to solve it on R. Okay. So your weekend problem is to solve this problem on R, but somehow you need a mass balance before you can solve it. Okay. I can't give this information into R and try to solve me anything. So since you said only mass balance equation, it makes it sound like it's a walk in the park for you, or like you're up to the challenge. Okay. Or anybody? Anybody ready to take that challenge? Come on. Okay. You'll give it a try? That's what we like. Okay. So I'll volunteer you and I'll volunteer her because she's okay. So you both can give it a try, and we'll have 3 lifelines. Okay. You can ask the audience. Okay. We don't have to phone a friend. You can just call a friend and ask. Okay. I can do a 50-50 for you if you want. Okay. So we'll do one of them. But let's go have a tea break and then come back and solve this problem. And over the weekend, you are going to write this in R and implement it.
It's very interesting. So what exactly required both water, environment, all fields we do. So let's have a tea break. We are already prepared. So today, since it is weekend is there, so the additional,
Yeah.
load for you. You have 2 more days.
So you
We'll
can
meet
work on
on
the
Monday, 2 o'clock in the afternoon.